Okay, guys. I think that we can get started. Let me just close the door. Today's class is going to be about security, and actually it's this class and next class. Actually, if you are doing the MSc program or the MSIT program, probably you've seen some of these slides in the analysis course, because when I was co-teaching the course, I actually developed this module based on the material that I normally teach in enterprise application integration. So if you've seen part of the material, please bear with me. Before we get started, I just wanted to give some pointers regarding the project, because some of you were asking some questions and probably not really taking the best approach regarding the project or the way it was being structured. So I was going to try on the board, but okay. Oh, sorry. I was going to try on the board, but then the people in Pittsburgh wouldn't be able to see, so I just draw some figures. So again, please bear with me. So one of the problems with this assignment is that if you don't really think about the deployment scenario, and if you don't think about how it's going to be used or how it would be used in real life, it's really easy to make mistakes in this assignment, because it's very easy to develop a solution that functions, which means that the functionality is there. But actually, if you wanted to deploy it, and if you wanted it to be scalable in a sense, or if you wanted the solution to be present, let's say, on an enterprise service bus, it wouldn't really work because of your decisions. And probably the biggest problem is that right now, many of you look at the assignment as being something like this. You have a web server and an application server, but you look at it as being just one application. So many people look at JBoss as being the whole container for everything, and don't assume that this can actually be deployed in several machines in different ways. And what I want you to think about is the implications in terms of actually getting the solution that you have and put it in a production environment. And if you look at the production environment, what you normally have, or what you have in many occasions, is actually the web server separated from the application server. And they can be executing in different machines, actually. And if you consider this, one of the immediate implications is that if you think about your session beans, the session beans cannot just offer local interfaces, because the local interfaces are only available inside the same JVM, the same Java virtual machine. This implies that if you actually have a business tier here, you need to think about what interfaces are remote so that they can be invoked, for instance, from the web server. Okay? Another thing that you should consider is that in a realistic deployment scenario, what you have is normally a load balancer in front of the system. This is a piece of equipment that, given a connection, is able to route it to one of the servers which is less loaded. And in many occasions, you do have several web servers executing with your presentation layer. And the same thing happens with the application server and even the database server. Again, the details vary a little bit from system to system, but realistically, what I want you to think about is a scenario similar to this one when you deploy the solution. So think about this and think about the implications. For instance, where do you think that authentication should be performed in your application? Do you think it should be only on the web server?
No, it's on the application server.
It's on the application server. Why? Imagine that you only implement authentication at this level. And basically all the interfaces that you publish here are available for anyone to use. If you do such a thing, basically the system is going to be very, very vulnerable. Right? Why? Because if you have someone in your organization, this person can connect to the application server and call whatever methods are available. Right? And that's a problem. Another thing, you should try to keep the control logic or the business rules at 0 or to a minimum on this side. Why? Because think about this. This is your business layer. This is where the processing occurs. So imagine that you want to put a standalone client alongside with this web interface. If you don't actually put the business rules and the business processes in here, what's going to happen is that you are going to re-implement all the functionality on the client application. And again, that's not what you want to do. And imagine that you actually want to put this application silo on an enterprise service bus. You can only do that if you actually have a proper interface, a business interface at this level. Okay? So be really careful about the way you design your remote interfaces and your local interfaces and your remote interfaces. Be careful about the places where you do authentication. Be careful about the way you manage the sessions. Okay? One thing is, for instance, to have a web cart, which is basically accumulating, let's say, purchase orders, and that's perfectly fine to be implemented, let's say, on the web server. But when you actually submit the request for making a purchase, it should be properly done and has a role at the application server level. Okay? So be careful about separating the things and designing it in a proper way. In this assignment, this is one of the most important things that you have to consider. Okay?
But I can assume some things, or can't I? For example, I can assume that the load balancer routes all the requests from a certain IP to the same web server, or not?
Okay, you can assume some things. Some of the things that you can assume. You can assume that this is a smart load balancer, which is the common case, which means that if a certain client connects to a web server, the load balancer is able to keep the connection to the same web server. Okay? You can assume this. What this means is that, for instance, in terms of your HTTP sessions, you just need to keep a normal HTTP session. Realistically, when you deploy these kind of scenarios, what you normally do is not that. So normally you don't rely on that kind of functionality, because if you did, if one of the web servers crashes, basically all those clients are crashed. That's one point. The second point is that once a client connects to a particular web server, that's the only web server it can use. So in many deployment scenarios, what you put in here is actually another component, which is a distributed memory component. So something like a Terracotta server or JBoss cache or something called memory cache DB. And what happens is that when you start the session, it's stored on a shared memory that is available to all the web servers. And when you get the session in your JSP, basically you are getting a session from a distributed cache. I don't require you to do this, but actually if you go to an enterprise and to a company, and if you are using this kind of technology, it's very, very likely that you will have a distributed cache on the web servers. Regarding the application servers, in general, the support for clustering is embedded in the application server itself. It's very, very common when you buy an enterprise license. One of the things that you buy is actually the clustering support. And the application server itself has the mechanisms to actually route that in a cluster. The same thing happens in the database server. So it's quite common to cluster databases, but again, the support for clustering in a database is embedded in the database itself. So you don't have to take that in consideration. The only exception, the most common exception to this is actually the web tier, where you normally have a different kind of middleware to manage the sessions in a distributed fashion. Okay? Questions about this?
No question.
People at Pittsburgh, is this clear?
Yeah.
Speak up.
Yeah.
Okay.
What kind of authentication are we expected to do at the application server and not on the web server?
What kind of authentication, or why are you expected to do the authentication?
No. What kind of authentication are we required to do on the app server, and what kind of authentication are we required to do on the web server?
So, basically the idea, you can implement this in several ways, but imagine that you have a stateful bin here on the application server, and before you can use any other method, you have to call a method that does something like login, username, and password, okay? And if it's successful, basically the user is authenticated, and because it's a stateful session bin, you can actually save inside of that session bin that user is authenticated. So when you authenticate on the web server, basically you delegate to the call to the application server. You save here a stateful bin that says that user is authenticated. You return the call to the web server, and basically you save the information that it was successful and is authenticated. Okay? So that's the normal way you do it.
I have a question.
Sure.
Usually the user can browse through the site without logging in, right? So do we
Yeah, you
allow
can-
that functionality, or do we by default assume that everything is like in a session?
You can allow browsing and adding things to a cart without having the user authenticated. That's not a problem. The only place where you actually need to have him authenticated is when he actually submits the order. So
Okay.
if you look at Amazon, the functionality that I'm asking you to do is very, very similar. Okay?
Okay.
The most important thing in this assignment is really the interfaces and how you design the system so that it's realistically deployable, let's say. Okay? Okay, guys. So let's talk a little bit about security. So security is one of those funny topics and very interesting topics, and actually a very, very hard topic. And the interesting thing is that if you look over the years, you see the same kind of problems appearing. You see people complaining about security vulnerabilities, and so on and so forth. So imagine if you go back to 2005 and you read the Dr. Dobbs Journal, which is a magazine for software developers and software engineers, you see, for instance, one of the reports saying that there was an out-of-bounds read in a particular buffer inside of the Linux kernel. And if you continue to read the same magazine, you see that, for instance, again, it's a bug in the kernel. It's a buffer overflow, which means that you can actually exploit it in a certain way if you write a negative link to the buffer. And you continue and you say, this one was actually a very, very interesting. No, it was not this one. But basically, it's not even in the kernel. It's also in things like players of multimedia and things like that where you can abuse the system. The one I was going to tell you about was this one. This is one of my favorites. It was actually a bug in the Internet Explorer where basically you could devise an image so that if your browser actually tried to read the image to show you, it could execute malicious code. And imagine this, you are just browsing a website, and actually inside an image of a website, there can be a code for a virus or for performing an attack on your system. And one of the things I would like to show you in next class is actually how you write code to do this, at least for you to get an idea on how it's done. But the main point I want to pass at this point is that all these guys, the guys that are writing the Linux kernel, the guys that are writing the Internet Explorer, the guys that are writing Microsoft Windows, they are actually smart guys. And they are professional software engineers that have been doing this for many, many years. And the same kind of problems still occur, right? And what's the problem? The problem is that, in a sense, the devil is in the details. It's the little things that you let pass that actually later on can be exploited to attack you, okay? And one of the important questions regarding this is that it's not all about code. It's how you control quality, and it's the kind of processes that you put in place to actually write secure code. You cannot solve all the problems, but you can actually improve the state of affairs if you are careful about. So what I want to talk about is basically the motivations behind security from an enterprise application integration perspective, and the kinds of things that I want you to pay attention. And what's the relevance of this? If you look at enterprise application integration nowadays, and if you think about enterprise service buses and so on, this is actually running on the internet. And the funny thing about the internet is that if you put a server on the internet or if you put a server on an enterprise service bus, sooner or later, and probably sooner, that server is going to be attacked, right? And when it's attacked, there are a lot of costs that you incur on. For instance, you need to develop new code to actually patch the problem that occurred, and this includes paying programmers to code, to document it again, to test it, and to do redesign. You have the cost of redistributing the patches. So imagine that you are JBoss, okay? And now imagine that you have, let's say, 10,000 installations or 100,000 installations. You have to pay the cost to actually send out the patches, and the people have to pay the cost of installing them, and so on and so forth. Another important cost is actually credibility. So whenever you publish a bug and whenever you have a security problem, basically your credibility goes down. And if it goes down, basically you are losing clients. And if you are losing clients, you are losing money. Okay?
Seems that Google already solved that one because they patch their software without without the user knowing.
Mm-hmm. Okay. So there are some techniques to alleviate this. For instance, in the past when you had standalone applications and you didn't have internet, this was really a huge cost because you actually had to send CDs and notify clients and so on. With online updates, it became easier, okay? But even so, you have a credibility kind of problem. With software as a service, this is actually improved because basically all the software is hosted and you can correct it in a sense on the fly. But again, in many production systems, that's not really an option because you cannot just move the software from version to version without the clients knowing. That's actually very dangerous in a lot of systems. Okay. So lots of revenue, lots of productivity. Why? Because if people are actually pinging you saying, we have a bug, we have a problem, you are actually losing time fixing all those problems instead of developing new functionalities, which will actually bring you the new money. And of course, there's always the possibility of lawsuits, which means that if you actually do a big mess and someone can prove that it was your fault, you can actually be sued in many occasions. These are numbers from 2002. 2002, basically the Microsoft Security Response Center estimated that every time they issued a security bulletin regarding a bug, that bug cost about $100,000. And these are numbers from 2002, okay? So this is serious money, and this is really a serious problem in terms of industry. And one of the focus of this class, and I strongly advise you to read this paper. It's really a fun paper to read, I think. It's why crypto systems fail, and this was kind of a landmark paper because what they did was to look at, I think it was 10-15 years of security faults, especially in the banking systems and in the ATM systems. So they were looking at banks in UK and seeing over 10 years how did people basically broke into the information systems of banks. How were they able to take money every time that was actually known to the public? And one of the most interesting conclusions that came out of this paper and this study is that the security model that is in the minds of many developers and many software engineers is actually wrong. And typically the mindset that people have when they are implementing security is that my system is going to be taken down, let's say, because someone is going to be able to find out the private key or is going to try a brute force attack to the system or something like that. And the model in general, it's what's called a fortress model. A fortress model is like, I have my house and I'm going to build these thick walls around my house. And all the attacks are going to come from these walls, from the outside of these walls. And what they've shown is that, in general, it's not these walls that are attacked. In general, what happens is that the software, when it's implemented, it has bugs, and the bugs are exploited. So I'm not trying to break the encryption mechanisms. I'm actually trying to find out what bugs are there in the implementation of the protocol. They found out that in many, many occasions, actually the systems are attacked from the inside, not the outside. Which means that if you have a large enterprise system, if you are running a bank, most of the attacks are going to come from your own employees. They are not going to come from the outside of the bank. And this has serious implications in terms of design, because this fortress model, where you trust all your employees and you don't trust the world, is actually wrong. Because what history has shown and what they found out was that actually, for instance, in banks, most of the attacks were being done by the technicians and the clerks of the bank. Okay? So you have to design the system to take this into account. Now extrapolate this to an enterprise service bus or to a service-oriented architecture. Somehow you cannot assume that the several systems that are intervening in a transaction or in a business process are safe, right? Why? Because, again, the attacks can be coming from the inside. And this is one of the reasons I was telling you. You need to do authentication at the business layer, not at the presentation layer. Okay? So, I strongly recommend that you read this paper. It's really good fun, and I don't advise you to do what they did. And there are some attacks there that can be still applied today. So keep away from that. But it's interesting information. Some examples. This actually happened in the UK. For instance, there was the case of a bank clerk that actually issued extra cards whenever a client came. Basically, he issued not only a card for the client, but also for himself. And he used these extra cards to actually take the money out of the bank. You may think that in Portugal this is really not possible because you receive the code later on and it's in a separate envelope and so on. But for instance, in the States, when I open a bank account, actually the PIN number was inputted. I had to write the PIN number when I was at the bank agency. So that PIN number, the clerk could actually look at the keyboard and see the number I was introducing. I actually have very good relationships with a telecom operator in Portugal, and last week we were just discussing the number one cause of fraud in prepaid numbers, where you actually have refills for the cards, is actually someone stealing the codes when they are printing them out in the typography, because basically the guys have the files and they are the ones that actually produce the cards, which means that if they actually keep the vouchers, they can sell them and they can give them to people. So it's very, very common to have this kind of inside attacks. Another example, this one in Scotland. Basically you have these technicians that go to ATM machines and do the maintenance. In this case, basically it was a technician that installed a small computer inside of the ATM, a handheld computer, and this computer basically would record the card and the PIN number being introduced because he had access to the ATM. As you know, in Portugal we have ATMs every place. It's really easy for a technician to do these kind of things. Another example, this one is interesting because it's not a description from a direct attack, but actually the consequences of management saying some things. In this case, there was a bank manager that issued a memo saying that some of the double security procedures of the bank would be abolished because of costs. And just by sending this memo out, although they didn't abolish the double security procedures, basically everyone started to try to attack the bank from the inside of the bank. I don't know if you know what's a double security procedure. Basically what happens in banks is that for certain procedures, the procedure cannot be done just by one person. It has to be done by at least two persons. For instance, I've told you that my father was a manager at a bank. The keys for the safe are not just with one person, are actually given to the bank manager and the sub-manager. And for opening the safe, they actually have to be both there. It's not only because they don't trust the bank manager or the sub-manager. There is another reason for this. Can you have an idea why?
Robert tries to get the money out of the bank. He needs to also.
There is
Okay, the two people have to be there, but did you wanted to say something?
It's availability or replication, something like that.
No, we are talking about the persons themselves. So if I'm a bank manager, I have a key for the safe. But my sub-manager, the guy that works for me, also needs to have a key so that we can open the safe.
So two-factor authentication maybe?
It's a way of authentication, of course.
Okay.
Press the button.
If some of person gets stolen by some terrorists.
That's right. Can you press?
Yeah.
That's actually right, and it's or at least it was in the bank manuals. One of the things that banks were really afraid was that if at night I go to the home of a bank manager and I tell him, I will kill your family if you don't go to the bank and open the bank and the safe, they were really afraid that the managers would be compelled to do that. And what happens is that it's a lot harder to coordinate this kind of activity, like forcing someone to do something, if you have two different persons and two different families at separate places, than it is for just having one person. It's possible, but it's a lot harder. That's the point.
Instead of one family, two families.
Yeah, of course. But the point was exactly that. So the rationale is that it's a lot harder to kidnap two persons or two families than it is to actually kidnap one. Okay, some examples of outside jobs. Some examples of outside jobs. In the past, when you had an ATM card, actually the identifier of the card in terms of the magnetic strip was based on the number of the card. And what some guys actually figured out, they knew the algorithm. Imagine it was a simple hash. So what they did was to actually stand in line behind someone, and when the person inputted the PIN, they would look at the PIN the person was entering, and then they would wait for the person to go away, and they would collect the paper, the statement that we normally leave at the ATM machines, and using the number of the account, they were actually able to generate a new card, and with the number they were able to take the money out. This is the reason why still today, if you look at the paper slip, the last numbers of the bank account are not written down. You see you have XXX. Have you noticed that on the paper slip? And this happened because of these kind of problems, because the number was generated using the bank number.
They could change the algorithm. But didn't they change the algorithm?
I'm not sure. I'm not implementing banking systems. But this was actually the problem at the time. Some other examples, using false terminals to actually record the customer card and PIN number. The most funny or interesting example was actually in a mall, and what they did was to put a cigarette machine on the mall, which would only accept a debit card, okay? But the machine was actually a false machine. Independently of the card that you put it there, it would always give you a pack of cigarettes. But what it did was actually very smart. They had a card reader, and basically the card reader would copy the card, and they have a keypad for you to introduce the number, and again, they would record the number, and basically with the information on the card and the key number, it's very, very easy to create a new card. Actually, if you look at the cards, the reader, it's just a standard reader. It costs you about $10 to actually buy it, okay? So these guys collected a large number of cards and a large number of numbers, of pins, and were taking money out of the ATM machines. So these are examples of outside jobs, so people that are attacking the system from the outside. Technical problems, and this happens, for instance, when you are actually implementing the systems. Some interesting examples. in the beginning, some people would not encrypt the connection in full duplex from the bank to the ATM machine, which means that the only thing that they encrypted was the response of the... Sorry. Okay, I'm not going to read it. But what happened in practice was that they would not authenticate the order. So basically, once you got a valid order, for instance, if the bank would order an ATM machine to pay $10, if they actually put something on the wire to collect the information being transmitted, they would be able to replay the message. And every time they replay the message, the machine would give money out. Again, this was an implementation and a design problem in the system. Another example, you know that every single system has test code, right? And ATM machines have test code. So this particular ATM machine had a 10-digit number that basically would force the machine to give money out, okay? And they didn't take this code out, and they actually wrote the 10 sequence number, the 10-digit number on the service manual of the ATM machine. Of course, some of the technicians read that, and they saw, does this work? Went to the ATM machines and started to jackpot the machines because they had the number. Again, if you think about this is not even a technical problem. This is how you structure the project and the kind of information that you let out or the kind of software that you let in the system. Let me tell you that this may seem funny in a sense, and you'd say, come on, I would never do this, right? It's not that easy. Let me tell you why. At least in avionics systems, for planes and things like that, there is this rule that you have to follow and is in the standards. And the rule is, you test what you fly what you test. Okay? And why? Because if you have a certification process and you need to have code to actually test the system, if you take the testing code out, basically the system that you have is not the system that you tested, right? Which means that the test code has to be there. By the way, every single plane that you fly today, all the testing code and all the infrastructure code is actually in the plane because of this regulation. So you actually can have you can have regulations that tell you once you certify a system, you cannot take that code out because the system would not be certified again. And think about voting systems, for instance, or think about avionics systems, or think about banking systems. In some cases, you really have to be careful about this. Okay? Okay, some other technical problems. This machine had a stupid bug where basically if you inserted a telephone card in the machine would think it was the previous card. So again, you could look at the machine, you could look at the pins, and when the person went away, insert the card and jackpot the machine. Another example, this programmer that had made a mistake, and this was at a time where you couldn't choose the PIN number, and what he did was to actually issue the same PIN number for all the customers. Okay? So every single customer of the bank would have the same PIN number. Of course, if you do this, basically, you own the bank. And this happens, right? Okay, a lot more examples. Another example. This is actually very common, this one regarding encryption. One of the tough things regarding encryption is actually testing systems that have encrypted data. Why? Because if it's encrypted, it's really hard to do testing. Okay? So one technique that these guys used was to actually always use the same encryption key, because then they could have a small piece of software that would decrypt it automatically, and that was it. And what's the problem? In the end, they always used the same encryption key, which again meant that the whole banking system was widely open for everyone to attack, as long as you knew this was going on. And other problems, this was also quite interesting. Whenever you have two banks, these are just examples for you to get a sense of what happens, but whenever you have two banks and you are setting up a system to communicate between the two banks, you have to set up what's called a zone. And the zone is a special machine where the two banking systems connect, and this special computer actually needs to have the encryption keys from both sides, okay? Why? Because it's like a demilitarized zone, and it's the kind of interface of the whole system. One of the very common problems is that people don't really understand what's going on. And in this case, what happened was that the consultant that was helping the guys to do this actually used his PC and turned the logging on, which meant that the managers of the bank were actually inputting the zone keys in his laptop, and he was actually recording the zone keys. And what this means is that, again, he had access to two banks at the same time and could perform a number of operations without any kind of problems. And another very common technical problem, be careful about this. In my students and even in professionals, I've seen this happen over and over and over again. Some people, when they are generating session keys to talk to another system, basically they use the time of the day as a key or some form of hash of the time of the day. And people think, oh, if I'm using milliseconds of the day, this is perfectly safe and no one will be able to figure it out. Well, it's not so. Imagine that you are trying to create a 56-bit key, which, by the way, nowadays is not that great. If you are actually encrypting or doing a hash on the time of the day, there isn't so many hours in the day. So what you are actually doing is creating a smaller key, because I know that the key was generated, for instance, this year, which means that a lot of the diversity of the number goes away. And I know that it was more or less in November, which again means that I can constrain the number I'm testing. And in the end, you get a key that is equivalent to about 20 bits. 20 bits, you can crack this in maybe an hour, something like that. Okay? So be careful about these issues. By the way, this is an important point. Whenever you need to implement something regarding to security, please don't try to do it from scratch. Please try to use libraries that are certified and libraries that have been in use for some time. Because what happens is that if you look at the protocols and if you look at the algorithms in the paper, they seem quite easy. But it's really hard to implement them in a correct way. It's really easy to introduce bugs in these protocols and algorithms, and when they are introduced, it's really easy for them to be exploited. So try to use software and codes that give you this kind of functionality off the shelf. Okay. Some other problems. Security by obscurity. This is done in many companies. Companies think that if they don't tell anyone about the specification of the software and they keep it a secret, no one is going to be able to attack it. Well, let me tell you that nowadays debuggers and things like that are really good. It's really not that easy, not that hard to break a system if you are trying to do that, if the system isn't safe. So when you design security, don't do it by obscurity, do it by designing the system properly. Another common assumption when you are implementing a system and the people that are managing the systems is that they assume that the software is perfect. The software doesn't have bugs. And when they try to basically protect the system, they are thinking about, again, encryption keys and things like that. And what these guys found out, and actually what industry knows nowadays, is that most of these security problems come from two places. Implementation bugs, design and implementation bugs, and the second one is human engineering. Again, it's not that hard to call someone and tell him or her, I'm not able to access the system, how can I do this, can you give me the password, or go to the actual physical place and look for the password under the keyboard or in a place like that. This is very, very, very common, and it's the easiest way to actually attack a system. Misunderstanding of technology. This is also very common, especially for non-technical people. If I go to a bank manager and I give him a key, and I tell him, this is the key for the safe, he understands the implications. If I give him a number which is 1, 2, 3, 4, and I tell him, this is the encryption key of the software, he doesn't get the point. He doesn't understand that if that number gets out, everyone will be able to access the system. And this is a problem even nowadays. So one of the things people discuss a lot is actually to have physical keys that store the encryption keys and the like. Because if I give something physical to someone, in general it's a lot easier to explain the implications. And the final factor, or another important factor, is the human factor. As I was telling you, it's really easy to engineer someone to reveal information that they have regarding the security of a system. And even corporate politics can have a huge impact in terms of the security of the system. Remember the example that bank manager said, we are going to eliminate some of the double control checks that we have. He didn't actually do it, and in the next month, the losses of the bank increased by 10 times. Why? Because people started to try to actually crack it. Okay? Okay. So, questions so far? No questions? Everyone is quiet? Okay. I strongly encourage you to read the paper. It's really a fun paper to read. It's not just to get to know the things. It's really interesting. Some basic concepts that you should know about. Authentication. Authentication is basically all the mechanisms that you need to have in place to identify someone in a system. Okay? When Higino logs into a system, the mechanisms that allow the system in all the application layers to know it's Higino are called authentication mechanisms. Authorization. Authorization is a different thing. Imagine that you have a system, and I know the users that are logged in. Higino, João, Inácio, and so on. Authorization are the mechanisms that, given a user, or given a principal can be a user or a different system, maps this user to something that he can do. Okay? And there are several ways of doing authorization. I can have access lists where I say, this user can do this, this, and that, but cannot do this, that, and that. Okay? I can have things like security tokens, like when I give a user a certain number, that binary string will fit a certain lock but will not fit different locks. That's also common. By the way, the NFS system, the network file system, uses security tokens. Once you have a token, you have direct access to files. You can have role-based security. What this means is that when I have a user, I associate him a number of roles like administrator, web user, database user, and then I associate to each role a set of permissions and so on. Okay? Protection. What's protection? Protection is guaranteeing that certain assets in my system are not used or abused by non-authorized users. Okay? Finally, security management. Security management are all the policies that you need to have in place to actually manage security. This includes things like, for instance, permissions, like if I'm in the internet, I cannot access the intranet of my company. If I'm inside the internet, then I can access everything. That's a type of policy. But it also includes things like how do I manage security breaches? So when someone cracks my system, what should I do then? Should I reinstall the system? Should I go back to a previous snapshot? Should I just correct the problem and carry on? Okay? Again, that's part of security management. Okay, let's look a little bit into protection. Core concepts that you should know about. Confidentiality. When people use this word, basically it means protecting secrets. There are certain assets in your system that you need to keep secret from certain users, being them authorized, being them authenticated or not. Integrity. What's integrity? Integrity means that no one is able to tamper with data. Okay? So imagine that you have, again, a database in a bank that represents the money that people have in that bank. While confidentiality means that no one is able to see what's the balance sheet of a particular person, or just some persons are able to look at the balance sheet, integrity means that no one is actually able to tamper with this data. Okay? Let me give you an example of how this is different from place to place. You know, there are people in banks doing data warehousing. Data warehousing is basically creating databases for business support. Seeing, for instance, how much money was being transferred during March, April, and May, and things like that. The people that are doing data warehousing, in many occasions, actually have access to the data. They can see the data, okay? But they cannot actually change the data. Why? Because the only thing they get is a dump of the database, or periodic dumps. So in a bank, they keep the operational systems separated from the data reporting systems, okay? And in this case, what they are trying to protect is the integrity of the system. Non-repudiation. This is also quite important. In some systems, I need to have ways of guaranteeing that when someone performs an operation, that user cannot later on denying having performed that operation. For instance, if you don't submit your assignment, I need to have a way to tell you, well, you didn't submit the assignment, although you actually didn't submit it and you are claiming that you did. For instance, for me, a non-repudiation mechanism for this is looking at the logs that the web server keeps. And I can see if you actually logged in into the system or not, or if you actually submitted the assignment or not. A digital signature is another example, okay? If you have a document and you put a digital signature using encryption, Again, later on, the idea is that you cannot deny that you haven't done it. Why? Because in principle, the private key associated to that is kept only by you. Protection, denial of service. In many systems, I need to protect them against denial of service. What this means is that if I have a system, I have legitimate users and people who shouldn't be using the system. A denial of service attack is when by some means someone is trying to prevent legitimate users from using the system, either by injecting load in my web server or by doing a ping attack or something like that. They are preventing good users from using my system. Protection. Security faults. If I'm properly designing a system for security, I have to take into account that my developers are going to introduce bugs into the system, and somehow I should have a way of dealing with that. One of the things that we'll see in the next class is a principle called defense in depth that tries to help with this. And finally, physical protection. Let me tell you that in systems that where money is actually involved or important things are involved, in many occasions people don't try to attack the system itself again through encryption or bugs or things like that. In many occasions people try to get physical access to the servers or the system. So physical protection is always something that I have to consider when I deploy a critical system. Why? I can have the best encryption in the world. If I put my server in a room that is accessible to everyone, I can just walk in, take the disk out, or access the console and mount the disk without any kind of validation. Physical protection, it's really important, and it's on many occasions the way people actually attack the system. Okay, some examples. This is not a security course, so I'm not going to talk about the techniques for doing this in detail. Actually, in no detail. You can take a course in security, but for instance, when I'm talking about authentication, I have technologies and methods to address that. I can use things like username and passwords. I can use Kerberos. I can use Active Directory. I can use LDAP. There are a lot of ways of authenticating users. Authorization. When I'm designing authorization, I can have things like access control lists, permission tokens, and so on and so forth. Confidentiality, I can encrypt data. Integrity, I can use digital signatures. Non-repudiation, I can use logs. I can use digital signatures. Denial of service attacks. This is a hard one even nowadays. I can use dynamic firewalls that change the ports or routers that try to block the attacks upstream. Again, there is no good solution nowadays for these kind of problems, even today in terms of denial of service attacks. Software faults, normal software engineering techniques, basically testing and validation. I can try to do formal proofs on my software. Physical protection, I can use locked doors. I can use encryption because if I encrypt the disk and someone takes the disk, I have a certain level of protection. Security management. Again, security policies that are written down, service level agreements with different companies, and so on. Again, if you want to learn about this, you can do a complete course on this, and you actually can do a whole master's on this and a PhD on this. There's a lot of work to be done. My main point when telling you these things is that security is not an add-on to a system. if you want to design a secure system, either you do it from the start, when you start to gather requirements and designing the architecture of the system and detail design, or if you try to do it later on, it's really, really difficult to retrofit it into a system. It's almost impossible. Or at least it's almost impossible so that you cannot attack the system. So please take this into account when designing a system. Let me give you just some ideas on how you do this. When you are doing security analysis, and this is something that a lot of people don't understand, a security analysis is always a trade-off analysis. What this means is that I can always deploy, let's say, more iron to the system. I can always put more things in place, more encryption, a bigger fortress, and so on. But I need to evaluate what's being attacked and what are the consequences of actually attacking my system. What this means is that if I'm writing a document which is a security analysis, or if I'm writing the requirements for a system, what I need to think is, let's consider I'm the enemy. And let's assume that I have a huge amount of resources and time to attack my system. Okay? The basic principle is, let's assume that it's possible to attack my system. And to do that, there's an associated cost and there's an associated time. And what I need to think about is, how much will it cost to someone to actually break the system? Will he need to use the supercomputer to actually break the encryption? Does he just need to use a normal PC because my encryption is way too weak and he doesn't need to spend a lot of time? Can he buy a disguise to enter the building and actually do this? I need to evaluate the cost of the attack. And I need to evaluate how much time it will take to actually perform the attack. Okay? And given these two factors, what I need to do is to evaluate what am I going to lose if the attack succeeds. Am I going to lose money? Am I going to lose data from my clients? Am I going to lose reputation? Okay? And the mechanisms that I put in place to address the attack should take into account this. Why? Because deploying security costs money. Okay? And let's imagine that I have a simple web server. The web server doesn't have anything really important. Imagine that it only has past date of some system that is not really used. Again, I can design it so that it's very, very secure and supports almost any kind of attack, but it may not be worth it. So again, I need to consider explicitly my possible losses. Okay? And if possible, I should quantize them. Okay? So, again, why do I do this? Because I want to make sure that I'm addressing the right problem in terms of security. I want to ensure that I'm actually protecting the right things in my system. And I want to ensure that I'm not over-engineering a system. Let me give you a funny example which is also related to this. When you talk about security, security also has a lot to do with human-computer interaction. And a lot of people actually forget this. I don't know if you've seen this video, but let me show you.
Hello, I'm a Mac. Mac is issued a salutation, cancel or allow. Allow, and I'm a PC. You're returning Mac salutation, cancel or allow? Allow. Okay, what gives? Mac is asking a question, cancel or allow? Allow. He's part of Vista, my new operating system. PCs have a lot of security problems, so he asked me to authorize pretty much anything I do. You're pointing out Vista's flaws, cancel or allow? Allow. I could turn him off, but then he wouldn't give me any warnings at all, and that would defeat the purpose. purpose. You are coming to a sad realization. Cancel or allow. Allow.
So my point is that when you are deploying security, you also have to be careful about things and about human-computer interaction. Why? What's the problem? If you over-design the system, especially taking into account humans, people are going to circumvent the system, right? So Microsoft did that with Windows Vista. They had this annoying thing that every time you click somewhere, it would put a pop-up there. And after a certain time, what do? Okay, you don't really read it. It doesn't serve any purpose after a while. Okay? And you need to be really careful about this part also. Let me give you an example. This was in UK also. And this is a very interesting story. This was a chain. Imagine something like, imagine a chain like Best Buy in the States or like Fortin in Portugal, where you have all these stores across the company, and these guys sell computers. And what happened in this case was that they hired a security company to actually make the system safer. And one of the things that they did was that they redesigned the way that people use the computers in the store. And what they did was that, if you have a store like Best Buy or Vorten, sometimes you have to demonstrate the computer and you have to log in and show a customer how it's used. What this company decided to do was actually to force every single employee to have its own password. And they even did something that was safer. What they said was that the password has to be changed every month, and it cannot be any of the previous passwords, because the system would be safer this way. Do you know what happened? What happened was that they started to have a lot of problems. Why? Because they work in shifts, and when someone goes away, goes home, and if he leaves the computer locked, no one is able to use the computer until next day, or they have to reset the computer, right? The second problem is that every time they needed to do a demo, they would need to see, who locked the computer? It was Antonio. And they would need to get Antonio back to unlock the computer. And this went on for a while. And this guy had this smart idea. I hate this system. Let me choose a password that is really easy and that I can change every single month. And what he thought was, let me put the name of the month and the year, like January 2009, February 2009, March 2009, and so on. Well, I always know the password. It's being changed every month. And this guy told the other guys at the store that he was doing that. And everyone said, what a great idea. And everyone started to use the same algorithm in the store, right? But after a while, what happens is that these guys actually change stores, right? They go to a different store and so on. And in something like 3 or 4 months, every single store in the whole country was using the same password. Okay? Worse than that, the management and the business managers of the stores were also forced to do this, to change the password every single month. And they learned about this trick. So it was not just the computers on the demos, on the displays, was actually the back systems that run the business. Okay? And this is an important lesson. Why? Because you have to consider the human in the loop. If you don't, if security gets too hard, basically people are going to find a way around security. And if you don't think about this from the start, basically you have a huge problem. Okay? Okay, guys. That's about it for today. Questions? No questions? Okay, great. Let's go.